Okay, so let's go ahead and this will be review for test number 3. Number 1. Question number 1, my friends. Question number 1. Question number 1. Ready? I have 150 amp feeder, 150 amp feeder. Feeder installed in rigid metal conduit. This is rigid metal conduit. The conductor inside it, so 150 feeder, rigid metal conduit. The conductors inside that baby, as there's 3 conductors here. Number 2-aught, 1 conductor, number 1, and 1 conductor, number 2. All of them are T, H, H, and N. All of them are T, H, H, N. And so this is the feeder. The question would be, could you please size conduit? Size a conduit that can carry these conductors. Size a conduit that can carry these conductors. A feeder has these conductors, 3-phase conductors, plus neutral, plus ground, and we need to size a conduit that fits. And the conduit type is rigid, right? Rigid metal conduits. And we need to size a conduit that can fit these conductors. You guys remember how we did conduit fill, basically? We have 3 conductors, number 2-aught, and I have 1 conductor, number 1, and also 1 conductor, number 2. And I'm not gonna, we go to chapter number 9, table number, all of them, these are going to be table number 5. Table number 5, to find the cross-sectional area of all these conductors. Cross-sectional area of all these conductors. What I'm trying to do, guys, I'm going to use it first, do it by hand, and then we'll do it via the calculator and see if we come up with the same answer. So, Chris, please correct me if I do something here. So, chapter 9, table 5, everybody knows how to go to this table, right? So, the first thing, I want to take 3 of these, multiply them by, I have the number 0.2223. Chris, am I right here? Multiplied by 1.1562.
Yes.
And multiplied by 1, this is 1.1156. All these numbers are coming from table number 5. So please, the installation is THHN, right? Everybody knows how to use table number 5 with installation THHN. Chris, did you check it with your table? Thank you. If you do the math on these, anything else in that conduit, there's nothing in this conduit other than this. You're going to end up with 0.9389 square inches. And I don't know about you, my friends, if you take the 0.9389, take this one to table number 4 under rigid metallic conduit. Rigid metallic conduit. And because how many conductors do we have? We have 5 conductors, so it has to be under the 40% fill. So this is also going to be 40% fill. If you guys go there, you're going to end up with a nice, beautiful 2-inch rigid metal conduit. 2-inch rigid metal conduit. 2-inch rigid metal conduit. 2-inch rigid metal conduit. Okay, what I'm going to do, guys, up to this point we're done with the test. Let me see if we still remember how to do it through the calculator. Did I come up with something? Anybody came up with something different? Anybody came up with something different, guys? Okay. All right, so I'm taking my calc here, my calculator, somewhere where it doesn't interfere with my business. I'm gonna move this slightly here. Take my calculator here so it doesn't interfere with my business. Okay, do me a favor, guys. Change your calculator to rigid. Set conduit. EMT. I can't remember what was rigid, so I'm going to keep going here until I set my conduit to rigid. FMC. IMC. Rigid. Come on, rigid. There's an easier way of than that. If we can find the.
I think
Is it number? Which number is that?
the code's
They have the number.
number 8.
Number 8. Okay, so it should be 8 set conduit. Okay, thank you. 8 set conduit is the number 8.
It's really handy, Chad. It's straight up here.
Is it also on the back of that one? I'm looking at that one. Okay, so awesome. So if you guys look at the back of your calculator, these are come very handy. Yep, right there on the back of the calculator. So it should be 8 set rigid mill conduit. Okay, so we're sitting at. Let's try the first 2-aught. Here's a 2-aught. 1, 2, wire size. How many conductors do I have? I have 3 conductors. And what's the size? THHN. And we said hit again. You hit twice the THHN, right? Let's do the number 1. Here's number 1. And wire size, number 1. How many of them do I have? I have number 1 and THHN and hit again. Here's another THHN. The second one, guys, is number 2. Wire size. And how many of number 2 do I have? 1. It's a THHN, hit again. And if you go to conduit, your conduit is 2-inch. The key point is when you put the number of conductors in the THHN, you hit the THHN again because the sizes are different. Does that make sense? Now in the test, guys, if you do it by hand, you do it by Excel sheet. If you do it by calculator, it's fine with me, as long as you do it. Thank you. I forgot that it's here. It comes very handy when always go when you're jumping around. Okay, any question, guys, about this? Did you come up with this? Should I do it one more time? One more time. Okay, let's do it one more time. So if you guys go to, first of all, I'm going to start with the first. I have 2-aught. 2-aught, the way you represent 2-aught is 0, 0. 2 zeros, right? And then you're going to hit wire size. Can you see it says 2-aught copper, right? Did you get this? 0, 0, wire size. Now I need how many of them do I have? I have 3 of them. And what type of insulation? It's a THHN, so 3, hit THHN. Now here's where you have to hit again because we have more than one size. Hit the THHN twice. So you get the fill for all these conductors. Okay, so we're done with the first 3 2-aught. Let's go to number 1. Here's again 1, wire size. So I have 1 copper. We're assuming it's copper. If it's aluminum, we change it to aluminum. It becomes aluminum. Okay, so we're done. Then how many of number 1 do I have? I have 1. And what type of insulation? It's THHN. Now here's 1 conductor, number 1 THHN. You need to hit again so you can get the fill for that boy. Here's the fill for number 1 conductor, number 1. We're done with number 1. Let's go to number 2. So what's the size? 2, wire size, right? Straightforward. Here's 2 copper, AWG. How many of them do I have? I have only 1. What type of insulation? THHN. What's the fill for that 1? Hit again the THHN, you get 158. So can you guys see that it takes every group of conductors and it find the fill for them? The key point is to hit the THHN twice. When you're done here, all what you have to do, the conduit is already set for you. You hit the conduit, rigid MC 2. Did they came up with 2.5? Did they make any mistakes?
I got the same numbers as You.
And you came up with 2?
Yeah.
I must have not cleaned mine. Okay, I must have not cleaned mine. Okay, let's do it one more time. Here's 0, 0, wire, right? And how many conductors? 3 conductors. THHN. Perfect. And hit this again. Okay, let's go to 1 wire size. 1 THHN. Hit this and again. And what do I have again? I have 2 wire size. And how many of them do I have? 1 THHN. THHN again, and hit conduit. Okay, I must have not cleared my calculator. When you're done, guys, clear your calculator by hitting the on/C twice. So 2. The key point, you know what, Nick, what I discovered with this calculator, the key point is to remember these little monkeying around. But the more you use the calculator, the more you get used to it. Okay, cool? All right, so I'm gonna use, I don't think we're gonna be using calculator for a whole lot. So 2-inch. Question number 2. Question number 2, my friend. An existing rigid metal conduit. I have an existing rigid metal conduit. And this is a nipple. Rigid metal conduit nipple. Nipple. So 24 inches or less. Contain 4 inside it there's 4 conductors, number 12 THHN, and 1 conductor also number 12, but this boy is bare, not insulated, and stranded. Bare, stranded, this baby, ground wire, and the size of this baby is 1 inch rigid metal conduit nipple. How many additional number 12 I can pull through that baby? How many number 12 can I pull through? So basically, you have an existing conduit. You need to find how many conductors you can pull through that baby. Pull through that baby. Okay? Does that make sense, guys? Does that make sense? An inch rigid metal conduit. There's 5 conductors in it. 4 number 12 THHN, 1 bare, stranded. And how many number 12 can I pull right through that conduit? I need extra to pull through them. The first thing you need to do, guys, is find, I call it occupied space. Space, the space that's already occupied. So I have 4 number 12. If you guys go to table number 5, chapter number 9, from this one, you're going to have a 4 times 0.0133. And then I have 1 number 12. Now remember, this is THHN. The first one is THHN. The second one is bare, so you need to go to which table do we go to find the bears? Table 8. This is kind of the tricky one because it's bare conductor. 1 times 0.006. Table number 8. Is it 700? What page, guys? Table number 8. Anybody? Okay, it's page 721. 721. If you guys look at that page, if it's 1, it's solid. If other than 1, it's stranded. So I have number 12 stranded, and I need the cross-sectional area. The area for it is 0.006. 0.006. Everybody knows how to find the 0.006 because that's we didn't go to table 5. We went to table 8 because it's a bare boy. Okay, if you add these, if you add them up, the occupied space is 0.006 0.592. Does it look like 9? 0.059 and 2. Okay? So that's my occupied space. Now available space. So for one did they say rigid? For you guys, rigid middle conduit. One rigid middle conduit. Which table am I going to go to? Table 4, 60-degree fill. I need help with that one. What's the rigid? Is it 0.575? Remember, it's 60-degree fill. Rigid, anybody there? Rigid middle conduit, 60-degree fill, 1 inch. 1 second. It's a 1 incher. 1 inch. How much fill you can fill it with 60 degree? 1 inch. You need 0.532. 0.532. Everybody can see that, guys? Rigid middle conduit. Inch. 0.532. 0.532. 0.532. Did they do it wrong? Rigid middle conduit?
I don't know where you got the 0.532.
Under 60-degree column?
Oh.
Because it's a nipple.
Oh, okay.
Guys, it's a nipple. You always go for 60-degree fill. 60%. So this is 60 degrees, 60%. Okay, everybody's there? 60%, 0.532. All right, so 60%. The third one we need to do is space to fill. Space to fill, as you guys can see, you take the 0.532 minus, I need somebody to do that for me, 0.0592. What's the answer, Steve? 0.532 minus 0.0592. 0.4728. Okay, so that's how much space I can fill. How much space I can fill? Is it right? So the math?
Yeah.
Okay. Then, how many conductors number 12, guys? What do you do to find conductors number 12? You take this number and divide it by the cross-section area of number 12. So, number 12. How many conductors number 12? You take this number, 0.4728, divided by, what's the cross-section area for number 12? We already found it. 0.0133. Anybody came up with something different? What's the answer? Divide these. It's going to be a big number. Anybody came up with the number?
31.8.
31.8. Now remember. Okay. Now remember, guys. If you're filling conduits, 0.8 goes where? Up. Less than 0.8 goes down. So I want you to give me exactly what you got. 31.
31.78.
Okay. Wow. 31.78. 31.78 is not 31.8, so that will translate to 31. I know it's so close. 31. 31.78, it's not 31.8. You don't go up in a conduit anyway. That will translate to 31. Nick, did we do anything wrong? Yeah. 0.0133 is the cross-sectional area for number 12. Now we're trying to find how many number 12. So what you do is you take the available space, guys, area, and divide it by the cross-sectional area of that conductor. So if I ask you tomorrow number 10, what do? You go to number 10 cross-sectional area and divide it by number 10. So this number, the question is, Chad, where the heck did you get this number from? This is actually coming from this, which is for number 12THHN, right? Same number, number 12THHN. So how many conductors can I fill? I can fill, my friend, 31. Any question, guys, about this? If I ask you how many number 1 aught you can fill, RH instead of THHN, you're going to go to the cross-section area of RH conductor, RHW, and for example, and divide the available space by it. So you really have three steps. Step number 1 is right here, and step number 2, and step number 3, and step number 4 to do this. First, find the occupied space for all the conductors, find the available space in the conduit, subtract the available space occupied from the occupied space from the available space in the conduit. That will give you what the leftover to fill. That's the space left over to fill right here. Then you divide this space by the conductor cross-sectional area, and that will get you how many conductors you can fill. Rob, any? You're not getting the same number? Well, it could be 0.4728. 0.4728 divided by 0.0133 equal. I came up with 35.5. So where did you?
I must have typed it in wrong the first time.
Okay, that's all right. Not a biggie. Not a biggie. We will. Not a biggie. So that's why I really like you guys to give me the answer. So this one came up with everybody came up with 35.5, and that will translate to 35. So I can only have 35 conductors. Thank you, Rob. 35 conductors. Any question, guys? Any question? What's going to change on the test is the conduit size, the conduit type, the conductor size, the conductor type. Maybe it's not enabled. If it wasn't enabled, where would you go? 40% fill. Okay, so this is, there will be a question about, guys, one question about conduit fill. Okay, let's go to the box fill calculation. Question number 2, box fill calculation. How many number 12 conductor can be pulled through a box, a square box? I have a 4 by 1.5 inch square box, and I have a ring, also a ring, and my ring is given as a 3.6 cubic inch. Added a ring. The box contain, this is my box. The box contain the following: 2 receptacles. So inside it there's 2 receptacles, 3 conductors number 12 conductors, and 2 grounds, and 2 number 12 ground conductors.
Sorry, Chad.
The what?
It's like a question about the last question, last problems.
Sorry, let's go back.
I don't know how to pick the right value for number 12 in table 8. How do you know that?
Number 12.
Yeah.
Number 12, Theater Chan, you will go to table number 5.
No, it's the next step.
This step here?
Where you multiply 1 by itself.
This?
Yeah.
Okay. Why don't you go to point?
You know, we have 2 values here.
1
I
second.
don't know which one to pick, and how you know the right one to pick.
That's on the table itself.
3. Because that one is bare. You talk about the bare one. Where did you get the 0.006, right? If you go to table number 8, guys. Good point. Good.
There's 2 values for number for each of the conductors.
Thank you. Each of conductors. The 2 values. One of them for solid and one for stranded. The first one is solid. The second, how would you know though? If you go to the 3rd column, do you see where it says quantity? Count 1, 2, 3. Do you see the word quantity at the top?
Yeah.
If it says the quantity is 1, that's solid.
Okay.
If it's 7, it's stranded. And you remember what I said, guys, stranded? So that's going to be other than 1, basically. So if you go number 12, right?
Yeah.
It's not the first number 12, it's the second because it's stranded. And go across all the way, and you're going to find that the cross-sectional area is 0.006, not 0.005. Very good point. Because why not 0.005? It's a stranded. If it has 1, it's solid. If it has other than 1, it's stranded. Everybody knows how to use this table, guys? Cool? Solid, stranded. Good point. Thank you. Sorry for that. So this one, basically, this number is for stranded. Come on, bud. Close the program. Too many things running at the same time, huh? Come on, bud. All right. Okay, good point. Slow us down a little bit.
Sorry.
I'm talking about my software, not you, man.
It's the same thing, and I found it, and I realized, why not?
Done. Okay. What happened to my... All right. Okay, everybody at the same point, guys. Sorry for that. All right. So the question is, how many additional number 12 THN conductor can be installed? Extra number 12 THN. How many? So really, the question: how many extra conductors I can bring? Just bring to the conductor. Bring to the box. Okay. How many conductors extra can I bring to the box? I want to use step number 1, guys. The first thing is available space.
space. So I have 4 by half square box. If you guys go to 4 by half for a square box, you're gonna go to table, which table? 314.16a, right? If you go there, you're gonna find the cubic inch for that baby is 18. And I have a ring.
21.
Is it 21? It's 21. Now what did they say here? An inch and a half, 21. Okay, 21. And what's the ring? Ring is 3.5, right? Add them up, piece of cake, you end up with 24.5 cubic inch. 20.
I think the ring's 3.6.
3.6 was the ring.
Did they say 3.6 my ring? Why am I lying to you guys today? At 3.6. What did he say?
I don't know. 12 hours of driving.
Yeah, 24.6. That's the cubic inch. Okay, 24.6 cubic inch. 24.6 cubic inch. That's available space. Any question, guys, before we go into the occupied space? Can I move to the occupied space? Give us enough room. Okay, so that's step 1. Step 2, occupied space is piece of cake. I have How many receptacles do I have, guys? I have receptacles, 2 receptacles. Multiply them by. I have they're all number 12. So what's the multiplier for number 12? 2 receptacles. You give them 2 and multiply them by 2.25. Right? Everybody knows where the 2 because there's 2 of them. Let me just put 2 here. And the second thing we need to do, I have 3 conductors, number 12, 1 for each conductor. I have to put, how many of them do I have? I have 3 multiplied by 1 for each conductor, multiplied by 2.5, right? And all your ground, equipment, grounding, conductor, all of them, they count as 1 based on 2.25. Anybody has any question with that? That's easy. First, you find the receptacle, 2 allowances based on the largest. All the grounds count as 1. All the conductors count as 1 based on that. All of them, each one of them will count as 1. If I did my math right, and I'm questioning my math after all this driving, as you guys said, 18? Can you guys check this number? 18? Okay. Okay. So that's step number 2. Come on, buddy. Close programs to prevent information loss. Close. Yes, but. Okay. So that's step number 2. Step number 3. Is my 3, my friends. So I have the occupied space, available space. What did we say the first one? We said it. Available space. Space to fill. Let's just say space to fill. To fill. The space to fill, guys, is a difference between them. What was the first one? It was 24.6. At 24.6 minus 18. 6.6? 6.6, right? Cubic inch. Right? I think you need to watch my math today. And then, so space to fill is 66. Step number 4, number 12. Number 12 to add. I'm going to call it number 12 to add to add, what do? You take the 6.6 divided by, what's the allowances for Mr. number 12? 2.25, right? I need somebody to do the math for me. I know my math is wrong here. 6.6 divided by 2.25 equal 2.9. 2.93. And since, can we go up in boxes? No, no matter what. This is not a conduit, this is a box. So what's your answer would be? 2. 2 more. And these are just either passing through without a loop or just coming and sticking there. 2 conductors. Any question, guys, about this? Any question about this?
Actually, a difference. If it comes through and the loop is less than 6 inches long, it's a one volume allowance.
Yeah, then one conductor pass through, that counts as 1.
Right.
If you don't make it a loop. So these 2 conductors, there could be 2 conductors just coming and sitting in the box like this, or it could be 2 conductors that are passing through the box. But I'm asking about bringing to the box. So these literally will be 2 conductors coming from anywhere else and just sitting right there in the box. Any questions about this? Let me do one more, then I give you a break. This one is going to be a pull box problem. This is going to be a pull box problem. Let me get rid of my email. Any question? Should I move? Oladipo? Good. So this is question number 4. Question number 4. Question number 4 is a pull box. Pull box, I'm going to give you guys a pull box like this baby here. And I gave you a very ugly one last time. This time is going to be probably as ugly. And here's what we have. We have conductors going this way and conductors going this way. This is the box that I'm giving you. And also, inside this box, I'm giving you a conductor that's coming from the back. This conductor actually is 1500 kcm, coming from the back. So, what's the question? The distance from the bottom wall to the top wall. So, as always, and I'm asking you guys to find the distances. We're going to call this is y, and we're going to call this is x. X. The distance between any, and I want you to find the distance between these conduits that contain. I'm going to call this is x1, and this is also x2. xy and x1 and x2. And the last thing I want you to find, please, is the depth. So if this conductor is to go in like this, continue, can you please find the depth? D. We need to find the depth. We're going to find the dimension, depth, width. We're going to find the dimension of this box, length, height, depth, as well as the distance between the conduits containing the same conductors. Any question, guys, before we start that one? This is not as ugly as the one that I gave you guys. From the get-go, do I have any straight poles? No straight poles. All of them are angle poles. Do I have a U-pole? No U-poles. Now, if I give you a U-pole, you guys, you know how to do it. 6 times the largest conduit engaged, plus all the others. Okay. So the first thing I would do is finding x. I'm going to work on x. When you're finding x, guys, you're looking at this wall. Can you guys see that wall?
That's where X. So looking at this wall, first of all, do I have a straight pole?
You have to give us the pipe sizes, so we're going no place fast.
Oh, thank you. That will help. All of them are 5 inch. How about that? 5, 5, 5. Yeah. 5 inches. 5 inches. 5 inches. 5 inches. All of them are 5 inch. Good point. 5 inches. Okay. All of them are 5 inches. So the first thing I'm going to say right here, no straight poles, right? No straight poles here. The second thing is angle pole. Angle pole. For angle pole, guys, how many angle poles do I have? I have 2 of them. 2 angle poles. So I can go to, if I'm coming from right, I'm going to call it right to top. R to T, right. Let's do it left, like based on what I'm doing here. It's left, depends where you're looking at. Left to top. Left coming from this side going up. Is there any left to bottom? No, it's just left to top. Okay, you take the largest conduit engaged in a U-pole. Which one is the largest conduit engaged in a U-pole? Both of them are engaged and both of them are 5. If one of them was 5 and the other one was 6, which one would you use? And both of them are engaged. So the largest conduit engaged, so that would be 6. From here, from this calculation, you're going to find 6 times 5 plus 5, right? 6 times the largest conduit engaged plus all the other conduits sharing the same wall. And we're looking right in here. Everybody see where we are? Looking right here. So that will be 35 inches. 35 inches. Any other U-pole, straight pole, any other thing that can give me X, think about it. The only way you can get X is if you're coming from left to top or left to bottom or right to top or right to bottom. Do I have right to top, right to bottom? Done. Can you guys analyze it? See how simple. It's only one pole. If I have another conduit from here that's going up or down, then it will be right to bottom, right to top, and I use a calculation. So the largest conduit engaged in a U-pole, plus all the other conduits sharing the same wall. So X is 36 inches. Is there anything else can give me X? Straight pole, U-pole, nothing. That's X. Y. Let's do a Y. Find Y. For Y, my friends, the same thing. No straight poles. No straight poles. Or angle poles, as a matter of fact. So the only thing I have is angle pole. I mean U-pole. Angle pole. Okay, so angle pole. To get Y, I have to go from top to where? To left. Do I have top to bottom? Straight. No. Top to right? No. Bottom to right or left? No. So my only option, my friends, is to go top T to left. It's the only option you have. Okay, the same thing, guys. 6 times the largest conduit plus all other conduits in the same wall. That will give me 35 inches. 35 inches. Is there any way I can find Y? Any other ways I can find Y? Any other ways I can find Y? So I just want to remind you also there is no straight pole or angle or U pole. There's no straight pole or U pole. There's no straight pole or U pole. Only angle poles. Did we come up with the same? Did your calculator come up with the same answer? Or your calculator is going to replace me soon?
Well, it's a little interesting when you want to compute the box size because of the X1 and X2. The
Yeah.
box size won't work.
But all the other dimensions don't work.
So
Pick the
let's do that
largest.
until we get to X1 and X2.
Okay. Any question about X and Y, guys? Any question about X and Y? Let's go find the depth. The depth, that will give me the dimension of this box. So it's 35 by 35 box.
The second one I want to find is find depth. For the depth, it's piece of cake. You have to take the conductor, which is given 500 kcm. You need to take this one to table 3 at 12.6, and under one terminal, under one terminal, and they'll give you 12 inches. Anybody can go there, please verify that's 12 inches. If you go to table 3, 12.6, under one terminal, would that be 12 inches? Remember, the conductor is 1500 kcm, big fat boy. So that's a depth. So my box is 35 by 35 by 12. These are the dimensions of the box. Make sure you guys know how to go to 312.6, please. Make sure you know how to go to table 312.6. 312.6. 1500. Chris, right? The last thing we need to find is find x1. Chris, is it right? 12?
Yep.
Everybody?
Yes.
Okay.
Yeah,
For this one. Okay, x1. I want to remind you, my friends, that x1 is actually the distance between the first conductor, x1, right? And so it's 5 times the largest of the two. So distance between them equal 5 times the largest of the two, which is 5. I mean 6 times the largest of the two. Both of them are 5, so 6 times 5 equal 30 inches. So the distance between them is 30 inches. The same token, if you go find x2. x2 is also 6 times 5 equal 30. And I'm just waiting for somebody to tell me, Chad, how are you going to drill these then? 30, 30. So you might, minimum is 30. You might have to shift them around. So the two x's are 30, right? Look at them by here. The distance, the largest conduit engaged of the two, 5 times 6, 30. 5 times 6, 30. Now how are you going to put them 30? If this is 30, this cannot be 30 physically, mechanically. It has to be more. We don't care. As far as we're concerned right now, it's just the minimum distance. Can you guys see that? Both of them cannot physically be 30. One of them has to be more than 30. If the first is 30, the other one has to be more than 30. Or you can adjust these one. You might have to be able to play with the distance. Remember these, you might be able to play with the distance. So as far as we're concerned right now, as the calculation will do, both of them are 30. Any question about the whole box? Yes, sir.
You said we should find the depth, but I think the depth should be like 35 times 12.
No, the depth, the only way you can find the depth of a box by code is if there's a conductor coming from the back of the box facing the front. It's the only way. If that conductor, look at back here.
No, what I think is that
If this conductor here was not coming from the back, facing the front, or you're facing it as you open the box, you cannot find the depth. Well, I guess you can by code. Then you have to say, well, I need a box that's deep enough to handle a 5-inch, plus all the lock nuts and the connectors. So probably you're looking at minimum of 6-inch box if there's no 1500 kcm coming in the back. Why? Because you need a 6-inch and you need to be able to make a hole 1/2 inch from both sides and do the lock nuts. Anyway, code-wise, the only way you can find the depth code-wise is if you have a conductor coming from the back. So please, this baby here, very, very important. This conductor coming from the back, very important. If that doesn't exist, you can't find the box based on the code anymore. See that conductor? Or conductors coming from the back. Any question, guys? Any questions? Okay, I'm going to give you guys a quick break. I have 10 of these problems.
So we're at 4. I have 6 to go. The rest of them are easier because it doesn't have tables and all stuff. Yes, sir. Break if you're good.
These things necessarily compute, would that box size work, or do you have to keep adding to account for spacing in order to get the X1 under 50?
Would that box work right now?
Yeah, with a 35 by 35 inch box fit.
If you can buy it, otherwise you're gonna go to next standard. Yes, should.
So these calculations imply that you can make the diagonals required. Is that true? I haven't done the math.
That diagonal, that's in the field. That's in the field as you, because remember the hypotenuse. Let me just stop myself here. That one.
No, I mean I know the geometry.
All right, let's go to the next one, number 5. Number 5 is a piece of cake. Everything is piece of cake to you, Chad. Okay. Okay. All right, why can't I get my screen? Don't want to hide it. Okay, here you go. Number 7. Question number 7. Question number 7.
What happened to 5?
Question number 7 minus 2. 5. Question number 7 minus 2. 5. What is the amplicity of each 10 carrying? I have a conduit. If we draw it this way, I have a conduit. Good point. I have a conduit. Inside this conduit, guys, I have 10 conductors, number 8, T, H, and H, and N. T, H, and N conductors installed in an ambient temperature equal 90 degree Fahrenheit. And all these babies are coming out of all these 8 conductors. 6, 7, 8. All these conductors are coming out of it. All of them are carrying current. All of them are carrying current. 3-phase. You can imagine they're 3-phase. My email. Close. Okay. Okay, so I need to find how much current can I pull out of these conductors. In a case like this, guys, we can't use a calculator, so we have to use the old method way. So what's the question is, how much current can number 8 carry under these circumstances? Under these circumstances. So here's how you always start, guys. I always start based on normal condition. Normal condition, how much current number 8 can carry? Number 8, T, H, H, N, under normal condition. 310.15, B16, under which column and why? Which column and why for this baby? If you don't know anything about this one, where would you default? 60 degree column. And why 60 degree? Because it's less than number 1 or less. Okay, well, how much current can I get? Anybody can give me 50? How much current can you get out of this one under normal condition?
60 degree column is
40. Number 8, you can get 40 amps. So keep in mind, no matter what, you can't get more than 40 amps out of this conductor unless you know the terminals are rated for 75. Then you go to 50. So no matter what, that's a normal condition. Now derating. For derating, here's what I would do, guys. Take number 8, T, H, and H, and N. Take this baby to 310 dot. Now they changed these. We're going to take this one, 310.15. 310.15 B16. 310.15 B16. How much current that baby can get you under 90 degree column? 55 amps. 55 amps. For derating purposes only, I can get 55 amps. For derating purposes only. Now remember, I have a conductor, I'm going for the amp, so I multiply. Remember how we used to divide by the rating factor? Now I have a conductor, I need the amps, I multiply. Okay, what's the derating factor for 8 conductors carrying current? Where do you go? You go to 310.15b, 3a, 7 to 9 give you 0.7. So then I take the 55 and I start multiplying it first by 0.7. Where did the 0.7 came from? From table 310.15b, 3a. Okay, then for temperature, 90-degree temperature, you're going to go to table 310.15b, 2a. For 90-degree temperature, 90-degree temperature, Fahrenheit, don't forget it's Fahrenheit. Your derating factor, 90-degree, is 0.96, right, Chris? Right, Phil? For 90-degree. So 90-degree ambient temperature, 87 to 95, I have 0.96. 0.96. 0.96. I'm sorry, the first one should be, I have 10 of them. This one should be 0.5. Because I have 10 of them, this should be 0.5, right? For 10, it's 0.5. 0.5. For 10 of them, it should be 0.5. Okay, if you do all this math, guys, you're going to end up, and you do the math and you calculate them, you're going to end up with 26 amps. 26 amps. 26 amps. And Phil, how much amps could I have pulled out of this baby had I used it under normal condition? 40 amps. I actually could have gone 50 amps if I guarantee that the terminals on both ends are rated for 75. So look how much I lost. The reason why I like you guys to think about the loss, because you're going to be the designers. The worst thing that could happen to you, Dustin, is you bundle conductors in an ambient temperature that's hot. Bundling in an ambient temperature that's hot, the worst thing that could happen to you. If you have a hot climate, don't bundle, because you lose a lot of amps. Yes, sir? 0.5 for 10 carrying conductors from table 310.15b, 3a. You see it? 50%. 0.5 is 50%.
And then, Chad, for 55 amps, we're going to multiply by, what did we multiply?
We multiply it by 310.15b. This number here, guys.
No, I mean from 40 amps, which we looked up in the table.
One second. 310.15b, 3a. This is coming from
okay.
3a. And this one coming from 310.15b. B2A. B2A. 3A and 2A. I'm sorry, what was it?
Oh, okay. Now I'm on 310.B2A, and I'm looking under ambient temperatures.
Yep,
Right?
on the right hand side,
Okay, under the
90 degree.
Celsius.
It's a Fahrenheit.
It's a Fahrenheit. Okay.
So you got to the right column. So 87 to 95.
Why do we know that?
Because the ambient temperature is 90.
Oh,
I'm giving you an ambient temperature of 90.
okay.
So 90 is between 87 and 95.
Okay.
Make sense?
Yep.
Good point. So 26 amps. You're doomed, basically. 26 amps that you can pull out of this conductor. Yes, sir.
What was the question of this?
The question is how much current you can get out of number 8 under these circumstances.
In general, is pipe cheaper than wire?
Yes.
So which one was the?
The amps, this is the amp. Yep. Which one is the answer, Chad? This is it. Yeah. The reason why I gave you guys this one, you don't have to do this, the 40, just to give you, to compare how much amps you lost. You lost almost half of the amps of that conductor.
Well, and after you derate, they can't wind up up higher than that if I get the story straight. What's he-
Yeah, if you want to size a conductor now to carry 40 amps, that's a whole different story. We just have an existing conductor. Under these circumstances, how much current you can get out of it?
But if my D rating from the 90-degree column was higher than 40, I'm still limited to 40, but unless the terminals are rated.
Yes. 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 If this came up with 50, you're limited to 40, no matter what, unless the terminals are 75. Any question, guys? Okay, let's go to the number 6 now. Question number 6. Question number 6, my friend, this is, if you have a 700 service with a calculated demand load, Phil, this is exactly what you and I were just talking about. Exactly. This, you pay attention a little bit to that one. Look what I have. I have a service. My service is 700 amp. I have a service of 700 amp. The demand load that's calculated on this service, the demand load as 650 amp. Demand load. Meaning if it's a demand load, guys, meaning if you need to, it's already multiplied by 1.25 or derated, everything is done. All the calculation done, solid. So you have the load and you have the amps and you need to size the conductors. So what's the question? The question is, what size 75-degree cover conductor would be required if paralleled in two? And I'm asking you, I need to parallel 2 sets. I'm asking you to do 2 sets. What size conductor can you carry this one for 2 sets? Now I want to remind you, Phil and I were just talking about this one. What is the next standard overcomputation device ever? 650. 700. That's where the conductor becomes a little bit less amps than the overcomputation device. So my overcomputation device is 700. My load is 650. The code is allowing you to size the conductor based on the demand, not the overcomputation device, up to 800. Very important. So let me do it. So how you should do it the following. So size based on demand load. Demand load. Okay. So I have my 650 divided by 2 because I'm asking you for 2. That will give me 325 amps, right? 325 amps. Take this one to 310.15 B16 under 75-degree column, and that will get me the conductor as 3 conductors number 400 kcm. 3 conductors number 400 kcm. Okay, don't forget that's also 2 sets. 2 sets of 3 conductors. Why 3 phase? Do I need a neutral? Yeah, maybe. So 3 sets. If I need a neutral, it becomes 4. Can you guys see that? Very important. So we size 4 runs, 3 conductors, 400 kcm, 2 sets. 2 sets.
You have the page number for that table, maybe?
Which table?
154.
Okay, now let me tell you one little thing, guys. Here, that little secret here. If they take the 400 kcm, how much current you can get? 310.15 B16 under 75-degree column. How much you can get for 400 kcm? Can you guys do that? 400 kcm? I can get 335. I can get 335 amps. Right? I'm just doing a check now. 335. How many sets do I have of this 335? I have 2 sets. So what would that give me? Give me 6 70. No? 670 amps. That give me 670 amps, no? 33, 60, 55.
I'm thinking back.
670, right? If you just check. Now, is 670, look at that. Is 670 more than my load? Yeah. So that's okay. That's what you need your conductor to be able to carry your load. Is 670 equal or more than the overcome protection device that protects it? No. This is okay up to 800 amps. Up to 800 amps, fine. Because ask yourself, what's the next standard ever 670? What's the next standard? 700. Is there any overcome protection device between 670 and 700? No. If there's one overcome protection device between 670 and 700, then you have to lower this one down. Say if there was 690, then you have to go change this one to 690. Very, very important. Up to 800. After 800, you start matching the overcome protection device to the cable to the overcome protection device. I do this more when we come to the commercial, guys. We do a lot of examples about that one. But right now for this exercise, you always size based on the demand load. Now,
Can you give me the page number for that table? It's 310.154.
154.
It's 310.
310.15 B16 is 154.
That's the page number,
154, yeah.
Yeah.
Thank you.
So that was TPS 154.
Oh, no, I'm
The way you
looking
wrote
at-
it looks like 154.6.
I'm looking at the table number you wrote.
Here,
Yeah, it's
That's what I'm trying to find.
this is 310. 310.15 B16.
16. Yeah.
B16.
That makes it was.
Yeah. 310.15 B16. 310.15 B16. This is going to be a second nature, guys. When we go to these tables, it should be a second nature for all of us. Okay. 310.15 B16. I don't want to confuse you. So tomorrow for the test, not tomorrow, the day after for the test, all what I want you guys to do is do the first size here. But take this. I want you, now this one is extra, you don't have to do it. Take this one here. Suppose I want to size based on 700 amp circuit breaker. So what you do is you need to take the 700 divided by 2. That will get you 350 amps. And if you go to 310.16, oops, 310.15 B16 under 75-degree column. 350, what would that give you? 350. 350, 350, 500. That will get you 3 conductors, 500 kcm. 2 sets. Can you see the difference? Do you guys see the difference? Sizing based on the overcome protection device. A lot of engineering firms will do it this way. They size based on overcome protection device. So be careful when you do engineering. They size it based on overcome protection device. Some contractors, rightfully so, try to reduce the cost. They take advantage of the permit that the code allows you, and they size it based on the load. As long as the next standard overcome protection device is that circuit breaker size. So if you size it, I don't want you to size it based on this, but a lot of engineering will size based on overcome protection device. There are 2 ways, guys, you size a conductor. You can either size it based on a load or size it based on overcome protection device. The best way, if it's non-motor, size based on overcome protection device, especially for panels. Always the best way. Now, up to 800 amp, if you know your load, they allow you to go a little bit lower, 1 step lower. Up to 800 amp. After 800 amp, by the way, you go 1000 amp, then forget about everything else. The blue will rule after higher than 800 amp. The blue will rule. Okay? Any question, guys, about this? Number 6. So how are you going to size it, Phil? You're going to be sizing it based on this. For the test, how do I want you guys to size it? Please size it based on the load. Just to help you, 240. Just to help you, 700. Where's my 700? Okay. Just to help you guys understand, suppose this number here was 550. Okay? Just hold your horses. Suppose this number here, the load, was 550. What's your next standard overcome protection device? 600. So I have two options. Either I have to go change the overcome protection device to 600, or I violate the code, or I have to size the cables based on the overcome protection device, which is 700. I promise we'll do a few of these as we go to the commercial, because more in the commercial part. But for the time being, size based on the demand load. Okay, any question guys about this? Any question? Okay, let's go to question number 7 now. Question number 7. Question number 7, guys. What is the full load current? I have a big fat motor, and my friend motor is 30 horsepower, and the voltage is 208, and it's a 3-phase system. And the power factor, all these are given as 95%. If miss efficiency is given as 80%. Okay, so this is the information about this motor. The voltage, and I need, what's the question, Chad? The question is find full load current. Find the full load current for this motor based on these circumstances. That's straightforward, guys. You either use your calculator to find the full load current. I'll show you how in a second. Okay, so the formula that you need to go is full load current equal for this motor, the horsepower multiplied by 746, divide everything by 1.73 times miss voltage times miss efficiency times Mr. Power Factor. And if you guys plug all these in, the horsepower is 30 times 746 to convert it to kW, 1.73 times the voltage is 208 times miss efficiency is 0.8 and Mr. Power Factor is 0.95. You do all the math on this one, you end up with 35 amps if I did it right. Done. Any question, guys? Let's do it with the calculator, because you can do this with the calculator. See if we can get that one through the calculator. Okay. All right. So suppose you're going to do this to the calculator, guys. Set yourself at 3-phase as always. So set number 3. I'm looking at 3-phase. I guess 75 doesn't matter. I know it's 3-phase. I like to, if I'm working at 3-phase, I like to put myself 3-phase, 75 copper. Okay? Yes, sir.
How do you come about 35 amps?
Yeah, I don't get
I was thinking about 80, but
I was getting 81.
Right.
I got it in
Plus or
1.7.
minus, yeah.
81.7.
No, you're right. What did you guys come up with?
81 amps.
I was just using a different voltage. So, okay.
Oh, we're using
I was using a 480. Okay.
Oh, okay.
I was using a 480 voltage. That's why.
Excuse me.
Yeah.
It's supposed to be
82?
yeah, 81.7.
Okay, then we approximate to 82. Thank you. Yep, 82. Anything higher than 0.5? 82 amps. 82 amps. 82 amps. We could have discovered it with the calculator. Okay, everybody's okay with that one? I was using a different voltage, sorry. My voltage was 480 here. 208. And I know why. Okay, let's go put this one in the calculator and see if we come up with the same answer, guys, right? You're gonna do it with me? Let's start with the voltage. What's my voltage? I want you to make sure they are set at 3-phase. Everybody can see that, guys? You're set at 3-phase 75 copper. Your calculator. Okay, let's go put the voltage. My voltage is 208. Here's my voltage, right? Perfect. So make sure you set your voltage. The second thing that you need to set is the horsepower. So hit 30. Right, I have 30. And there are 2 horsepowers. Can you guys see that? Don't use the top one. Use the bottom one. The hypothetical, the theoretical one. So 30 horsepower. So I have 30 horsepower. The second thing you need to find is the efficiency. What's my efficiency? 80. And where's my efficiency? You have to go set and miss efficiency. Here's your efficiency is 80. Your power factor is 95. 95. And where's my power factor? My power factor is set watt. That will give you power factor. Anything else I need to put? 3-phase. The calculator is already set for 3-phase. I put the efficiency up by set. And if you hit the amp, you end up with, is that what you came up with, guys?
Yes.
That's cool, isn't that cool? So I could have discovered my mistake so easy now by 480. Oladipo, did you come up with something different? Shall we do it one more time?
Yeah.
Okay, clean, clean, clean. Let's clear it. Okay, the first thing you need to do is voltage. Make sure you hit 208, type 208, right? Hit voltage. It says at the, see that at the upper right left corner, it tells you the voltage is set at 208. Done with the voltage. Let's go to the horsepower now, 30. Don't clean anything. As you jump from one to another, don't hit any clean. So 30. There are 2 horsepowers. You guys see the horse HP motor? This is what we're going to be using tomorrow when I go over sizing disconnect and all this stuff. This, you need the HP theoretical one. So you're going to hit that one. Does it say HP horsepower TH? That's what the one that we want. The one above it, you're going to see how we're going to use it tomorrow. Okay, so the second thing, so I have my horsepower. Let's go efficiency. 80. Here's my efficiency. 80. And efficiency, you have to set and hit the hypothetical. You know what? When set to access the blue stuff. So here's my efficiency power factor. 95. And the same thing, 95 set watt. That will get you the power factor. Anything else? 3-phase. Some of you ask, where's the 3-phase factor, guys? Remember, my calculator is defaulted to 3-phase. If it was single-phase problem, make sure you default it to single-phase. And then you hit the amp, and I hope we get the same answer. Okay? That comes handy for this type of problems. Chris, did you come up with the same answer?
Yeah.
Okay.
I was just comparing single phase to 3-phase.
Yeah. Now, the mistake that your friend Chad did, the reason why I came up with different, I think I put 480, and I hit volt. Now my voltage is 480, and my answer is 35. That's how I came up with 35, because my voltage was 480 that I calculated in this sheet. You can put any voltage. If your voltage is 240, so I changed my voltage to 40. For the same problem, here's my volt, and I want to find what my amp would be. Here's your amp at 240. See how nice you can run scenarios, guys? What voltage is better for you or whatever. Okay, so that's with that. Let's go to, we killed this baby here. Let's go to 7, 8. Let's go to 8. We're almost there, guys. Question number 8. Question number 8 is piece of cake. I have a primary and a secondary transformer, and I have questions for you.
Here's my transformer. My transformer on this side is 208. On this side is 600 volt. Step up transformer voltage. It's a 3-phase boy, and it's rated for 1000 kVA. 1000 kVA transformer. Okay? So that's the transformer that you have. I want you to find the following. We're going to find 3 things for this. I want to find, number 1 is turns ratio. Number 2, we need to find I primary. And number 3, I secondary. These are the 3 things I want to find for this transformer. And then done. Very piece of cake. Okay, the turns ratio, guys, is V primary over V secondary. You can get 208 over 600, and if you flip this, it becomes 1 to almost 3. How do you come up 1 to 3? If you flip them, just make the 600 over the 208, right? Just to make it a ratio, it becomes 1 to 3. 1 to 3. Almost 1/3, right? 208 divided by 600. Take inverse, shift it. Almost 1 to 3 ratio. Any question why I came up with 1 to 3? After you divide them, you guys know how to find the reciprocal of a number? 1 over, that will get you 1 to 3. Or from the get-go, start 600, the highest voltage divided by the lowest voltage. That's a piece of cake. Second one, my friend, V primary. You're going to take the 5000K, divide this one by 1.73 times the voltage in the primary is 208. That's it, right? kVA divided by the I primary, 208. I came up with 2779. 2779 amps. I secondary is 1000K divided by 1.73 times 600. It's a step-up transformer, and came up with 963 amps. 963 amps. Anybody came up with something different? Now let's do it in the calculator. You can't find the turns ratio, but everything else should be able to find it. I should have kept it on. Here's my calculator sitting right here. I want to remind you, is it a 3-phase? Make sure you guys set yourself at always set 3-phase 75, right? So my calculator is set 3-phase 75 copper. That's exactly what I have. Is this system 3-phase? Yep, this system is 3-phase. This is how I'm going to find, you can't find the turns ratio from here because it's just division. You can find the I primary and I secondary. I'll show you how easy it is to find it. First of all, any question about doing it by hand, guys? Any question about that? Did we come up with something different? Phil, are the numbers wrong?
No, when I punched the calculator, I was 2075.
Okay, let me just do it together for the calculator, okay? First of all, you need to clear your calculator. So hit clear. Remember, we were working on it. Make sure you clear your calculator, right? A couple of times on clear right here. All right, let's go set the voltage. First, let's set the voltage. My voltage is 208, right? And hit voltage. Everybody's okay with 208 voltage? All right, now what's the size of my transformer? It's 1,000. Look how I'm going to put the kVA, guys. 1, 0, 0, 0, right? And do you see where it says K? Hit K. That will give you 1,000. Instead of putting 1,000, you put hit K and hit volt amp. So that will indicate to the calculator that you have a 1,000 kVA. Cool? And my voltage is 2.8. Now, I put the voltage 2.8, and I need to find the amps. What was the amps? The amps is, for this one, is 2775. 277, is that what you guys come up with?
Yeah.
Okay. And I think the approximation is slightly different because of 1.732. So 2775, like 2776, I have 3 amps difference. They're probably coming from the 1.73 factor. And we're not, when you have close to 3,000 amps, are you and I going to fight over 3 amps? So that's really coming from the approximation. No, so that's a primary. That's the primary. Let's go find the secondary. All what you need to change now is just the voltage. What's the new voltage? 600, 600, right? Put the voltage. Don't do anything other than change the voltage. And hit the amp. And you should come up with 962. And I came up with 963. Is my calculation here right, guys? Did anybody came up with what I came up with here? What did you come up with? Maybe I am off. So 1,000 divided by 1.73 divided by 208 equal actually 27790. Times, okay, I have 2779. I came up with 2779. Anybody came up with something different, guys? 28. Okay. So the approximation is a couple of amps differences from 1.73. Any question about this? Any question, my friends? Do you want me to do it one more time? We're cool? Using the calculator. You don't have to use the calculator on the test, but it comes handy. Okay. All right, let's do question number 8. 2 more questions, very simple, guys. This one is very simple. You're gonna number 9. Question number 9. Question number 9. A department store continuous load feeder supplies a lighting load of 165. Okay, so I have, this is actual size. I have a load here. My load is actually 165 amps continuous. And what's the question, Chad? The question is, could you please size the conductor, number 1, and number 2, size the overcompression device. Size the conductor and the overcompression device. We will do it. That's it. Just size. I have a load. I added all the amps for the load. It doesn't really matter if it's single phase or 3 phase or whatever. I have the amps.
Is that 165?
165, yeah. The 5 is just crooked a little bit. Okay, so the first thing I want to find, guys, is number 1. Number 1 is feeder size. And I'm not going to tell you that if it's 1.25. Anybody knows why 1.25 times the load? Continuous load. Now we got that one right. That will give me 206 amps if I did my math right. And then you take the 206 amps, take them to 310.15B16 under 75-degree column. And we all know why 75-degree column. More than 100, and that will get me a healthy 3 number 4 aught. 3 number 4 aught. Did you guys come up with something different? The second thing you need to do
as number 2 over current protection device. Same calculation. You take 1.25 times 165 equal 206 amps. Take the 206 amps this time to 240.6. If it's not a standard, where do you go? Go up. What's the next standard? 206 from 240.6 NEC. 225? 225 amp. 225 amp. 225 amp. Okay? 225 amp. Any question guys about that? So sneaking the calculator up, grabbing it up here, clear your calculator, and let's go do it. Does it really matter if it's single phase or three phase here? So what's my amp? I have 160. I'll wait a few seconds here until. Cool. Okay, so what's my amps? I have 100. What's my load? So Chris, we start with my load. My load is 165 amp. Now, Phil, is this a continuous load? If it's a continuous load, then you're gonna hit set instead of hitting the wire size. If you guys look at that, hit the wire size now. Oh, we didn't put the amps. Okay, so 165. I need to put amps, 165 amps. That's all what I need. It's continuous. Because it's continuous, I'm gonna hit set and then wire size. Here's your 4-aught, right? If you hit wire size by itself, if you guys hit wire size by itself, it will give you this. And if you keep hitting it, it tells you where you got the KCM and the table. See where it says it came the table 310.15B16. It's okay, 4-aught. And it will tell you, if you look, Phil, it will tell you its size based on 125. That's it. Overcap protection device, you can't size it from here. Unfortunately, I wish it has a button where it tells you the same thing. Should be just one button will tell you size overcap protection device, give you the actual size. Doesn't have it. No, overload is different. And you're going to see that we're coming. We're coming to this next week. Okay. Everybody came up with this. The last one before I let you guys eat. And we'll do it. Last one is very easy. Question number 10 and the last one. Question number 10 is the last one. The question would say, I have a fat, fluffy motor, 500 horsepower, and find KW equal. See how easy that is? That's a bonus. I have a 500 kW. How many 500 horsepower? How many kW is this boy? I want to convert mechanical energy 500 horsepower into electrical energy kW. Everybody knows how to do that, right? Multiply by what? 746. We're going to do it with the calculator, and we're going to do it with the. So the question would be KW equal horsepower multiplied by 746, based on the smarter than Chad people who did them long time ago. 5 horsepower times 746. That will, remember, it's a KW, so it's going to find, your answer is going to be divided by 1,000. Did you guys came up with 74.6? No, it shouldn't.
373.
How much?
373.
373 kW. Anybody came up with something different? Okay, let's see if we can get that one with the calculator here. That's the last one. Okay, so I've never tried that one, guys,
but I'm going to use 500 horsepower. Let's clear it. I always like to clear, right? Let's do a 500 horsepower. 1, 2. Make sure you hit the horsepower. And then all what you have to do is hit the watts. Did we come up with the same answer? 373? Right? Did you guys come up with the same answer? Did it? No?
Does it matter what phase?
Doesn't matter what phase or anything. Let's do it one more time. Why don't you clear your calculator? Clear your calculator. Put your 500, 0. Make sure you hit the right horsepower though. Chris?
Motor or?
It's not motor.
You want theoretical?
I want theoretical. Yep, hit the theoretical. And care less about the voltage because we're going power to power, apple to apple, and hit the right underneath it, the watts. 373.
You get forced in.
I get forced
Yeah.
Do a clear all, it's set, then clear all, and that's what did it for me.
Is that okay? Can you guys set clear all? Set X. Can you do a set X? I don't know.
Must have been left at 125% back in
Oh,
this one.
yeah, all of
Yeah.
those other.
And it didn't clear it from the couple of clicks
I
here.
don't think it'll.
It shouldn't
might not
affect
clear
it,
the
though.
power factor and the efficiency stuff.
Okay, set clear all. Cool. So we're all clear. It really doesn't matter if it's 75. Let's go to the 500
Yeah, I wouldn't sign that for clear all.
horsepower theoretical. Watts is 373. Yeah, if all hell break loose, guys, always use clear all. Clear the whole memory. I care less about the conductor, the temperature, and all this stuff. Any question? We're gonna go, guys. I'll get you for lunch, and then after lunch, I'll go. I need 15 minutes to go over the theory. Only 15 minutes. Thank you.